In this lesson, we will see how to add tolerance to the dimension. Why we need to add tolerance dimension? Point number 1, it is impossible to maintain strict degree of accuracy due to inaccurate manufacturing methods. Second point, in a mass production, we cannot able to maintain the same tolerance all the times. The third point, it is impossible for an operator to always make perfect settings or the same settings throughout the manufacturing process. Hence, we need to apply tolerance to the dimensions we specify. How to apply the tolerance dimension? Normally, to accommodate a tolerance dimension, we will add a plus or minus symbols to show the margin of errors. Otherwise, we can see a tolerance is a compromise between the accuracy required for proper functioning and the ability to economically produce this accuracy. Tolerance is the total amount that a specific dimension is permitted to vary. It is the difference between the maximum and minimum limits for the dimension. Tolerance can be specified in 3 places. 1. Directly on the dimension with a plus or minus symbol. Second, it can be added as a general note. Third, it can be added in the title block, or we call it as a tolerance block in the title block. For example, if you apply a dimension which is given as 1.625 with plus or minus 0.002. That means the manufactured part should be between 1.627 inches or 1.623 inches or anywhere between this limit dimension. You can see this, the tolerance is applied as a plus or minus symbols in the drawing as shown in the left. The tolerance is applied in the title block as shown in the top right. The tolerance can be applied as a general note as shown in the bottom right. What are the ways of expressing the tolerance? It can be expressed in many ways as shown in the slide. If you want to apply a uniform value of tolerance on both the positive side and the negative side, then we call it as equal bilateral tolerance. If you want to apply the tolerance value or different tolerance value in the positive side or the negative side, then we call it as bilateral tolerance. Generally, we apply a equal bilateral tolerance for most of the values. In a specific case where we have a constraint in one of the positions, then we go for a bilateral tolerance. There are other ways where you apply only the uniform tolerance on one side, or in other cases we apply a unilateral plus tolerance. In this case, there is only a tolerance value applied on the positive side, there is no tolerance on the negative side. So, you can apply this unilateral plus tolerance normally for an object like hole, because the hole value should have the minimum dimension and there it can only go for a positive values. When you go for a drilling operation, if there is any error in the drilling operation, it can only increase the hole size, it definitely cannot decrease the hole size. Generally, for representing a hole, we always go for unilateral plus tolerance. There is the next case we apply as a unilateral minus tolerance. Take the example of dimensioning a shaft with tolerance value. Whenever a mistake happens when you are manufacturing a shaft, it can always have a reduced value, not an upper limit. So, when you are representing the dimension of a shaft, you will always have a negative tolerance value, not a positive tolerance value. That kind of representation we call it as unilateral minus tolerance. Instead of representing the tolerance value, we can directly represent as a limit. We call it as the plus limits or the minus limits, or the plus limit in a single line or a minus limit in a single line. In case if you want to apply the tolerances for the assembly, we can apply in 2 ways. We call it as the interchangeability function or the statistical approach function. Both these things we will discuss in detail at a later stage. Traditionally, when you want to apply a dimension and tolerance, it can be done in either of these 3 ways. Engineering driven design, where the tolerance is normally applied by the design engineer, or when you create a process designs where the tolerance values are actually specified by the production manager or the production engineer. When it goes for an inspection driven design, the tolerance values are normally specified by the quality inspectors. When you apply tolerance, you should also take care of the manufacturing process and the cost involved because of this tolerance increase or decrease. Whenever we reduce the tolerance value, we call it as a tight tolerance. When you have a tight tolerance, the quality will be high, at the same time the manufacturing cost will be more. If you apply the higher tolerance value, we call it as a loose tolerance. When you apply a loose tolerance, the cost of the production will be low, at the same time you have to compromise on the quality. So, as a design engineer, you have to check what kind of tolerance value, whether it should be a tighter tolerance or it should be a loose tolerance, or it should be ranging in between these two, should be decided properly. Now, we see how to apply this tolerance value. We have seen the importance of tolerance. Now, we will see what value of tolerance we have to apply for each dimension. For that, we refer to something called as IT grades. What is IT grade? It stands for International Tolerance Grade. Based on the history of information available, the International Standards Organization have actually created this IT grade. Okay, the IT grade is referencing to the ISO complement of 286. Different IT grades are followed as per the manufacturing of objects. We use a IT grade of 01 to 06 for production of gauges and measuring instrument. We use a IT grade of IT5 to IT12 for fits and for fits in precision and general engineering. For semi products, we apply a IT grade between 11 to 16. For structures, we apply a IT grade between 16 to 18, and for non-tolerated dimension, we apply a IT grade between 11 to 18. This is how the chart of an IT grade will look like. This is the zoomed portion of this IT grade chart. Similarly, when you want to apply an IT, the tolerance value, it has to be decided on the manufacturing process. For different manufacturing process, the IT grade is specified. For example, if you want to apply a IT grade for a honing process, it should be between IT grade 3 to IT grade 5. If it is for a casting process, then it should be between IT grade 14 to IT grade 16. So, first step is you have to decide what is the manufacturing process you are going to follow, and next you have to find out the looseness of the fit, and based on it we will be determining the IT grade. Let us have a small workshop to just explain this need. Here is the object, here are the dimensions for the object. For these dimensions you have to apply the tolerance grade. Let us see what is the tolerance grade you have to apply for this. You can see this is a plate with a hole. The plate is actually finished by a milling operation, and the hole is finished with a drilling operation, but the plate has to apply with a loose tolerance, and for the hole you have to apply a tight tolerance. So, how can we format this? The detailed information on, okay, now it is a duty to complete this task. The result of this workshop you can cross verify in the completed information sheet which is available in the ORG site. Next stage is limits. Limit explains the upper deviation and the lower deviation which is given for the model. Right? You can see the picture which is explaining the limits of the structure. There are some key terms which we follow in the limits. Nominal size. It is the general size which is used for the identification of the feature. Then we have something as basic dimension. It is a theoretical size from which the limit of the size are derived. Actual size, it is the size of the finished component. What is limits? It is the two extreme permissible sizes between the actual size and the deviated size. The top portion of the limit we call it as a maximum limit. The lowest value of the limit we call it as the minimum limit. The difference between the maximum and the minimum limit we call it as the tolerance value. The difference between the basic size and the whole of the shaft size we call it as a deviation. The upper value we call it as upper deviation, and the lower value we call it as lower deviation. The line from where the deviations are measured, or the line which represents the basic size, we call it as the zero line. The grades of tolerance is a standard from where the deviations are measured from. In a clearance fit, the minimum clearance is called as the difference between the minimum size of the hole and the maximum size of the shaft, whereas maximum clearance is referred to the difference between the maximum size of the hole and the minimum size of the shaft. In the interference fit, the minimum interference is called as the difference between the maximum size of the hole and the minimum size of the shaft, whereas the maximum interference is the difference between the minimum size of the hole and the maximum size of the shaft. Okay. Now, you have to complete workshop number 4. In this workshop, you have to calculate the IT tolerance for an object which is having a diameter of 500 mm for the IT grade 10. Once you complete this workshop, you can verify the results with the completed results which is available in the ORG page. After completing workshop number 4, you have to start working on workshop number 5. In workshop number 5, questions are given to you. You have to complete this fill-in areas. Once you complete this, you can verify your answers as per the completed sheet which is available in the ORG page. Next, we will discuss what is meant by fit. So, when you take about an assembly product, you have normally two parts to assemble. At a single stage, we will have two mating parts. One is actually called as the hole part, the second is part as the shaft part. So, when a hole is inserted in the shaft, we may have three kinds of fits. The first fit we call it as a clearance fit. In the clearance fit, the hole size will always be bigger than the shaft size. For example, if the hole size is 10, the shaft size will always be less than 10 units. The next fit we call it as the interference fit. In an interference fit, the shaft size will always be bigger than the hole size, where the shaft size will be tightly fitted inside the hole and it will be rigid in nature. Where we have this kind of interference fit, when we insert a hood into a hammer, that fit we call it as an interference fit. An interference fit, it will not be easily pulled out. So, how to insert a shaft which is a bigger diameter value inside a hole which is a smaller diameter value? For that we use a kind of manufacturing process like heat treatment, where we slightly heat this shaft and we press fit inside this hole. That is how the interference fit are created. If you have any fit which is in between this interference fit and the clearance fit, we call it as a transition fit. In this fit, at one stage the hole diameter will be more than the shaft diameter, in the other stage the shaft diameter will be more than the hole diameter. This is how the interference transition fit will be created. Right. You can see the different types of interference fit and transition fit, and the clearance fit is available as per the charts. Normally we use these combinations as per the conditions given. For a loose running fit, we use a combination of H11 and C11. For a force fit, we use something as N7 and U6. These are the type of combinations we use. These charts are available in your data book. Now you have to complete workshop number 6. In workshop number 6, you have to find out the deviation or the fundamental deviation of a circular hole which is 40 mm in diameter, and it is finished as per H7 tolerance. In the second question, you have to find out the fundamental deviation of a circular shaft which is of 80 mm and it is finished up to G6 tolerance. Once you complete this workshop, you can verify your results with the completed sheet which is available in the ORG page. In this chapter, we will see how to determine the system of fits. The system of fits is divided as a hole basis system and a shaft basis system. This is how the hole basis system is explained. You can see this, the hole size will be equal to the basic size and the shaft size will vary, and based on the variation of the shaft size, we will find out whether it is a clearance fit, interference fit or a transition fit. In shaft basis system, you see that the basic dimension is equivalent to the shaft dimensions. We will vary the hole size, and based on the size of the hole, we will determine whether it is an interference fit, clearance fit or a transition fit. In most of the cases, we always prefer the hole basis system because it is easy to vary the shaft size by just turning it out, whereas if you want to increase the hole size, we have to use the drilling operation, which is a costly manufacturing process. So, internationally many people prefer to follow the hole basis system. In hole basis system, the H is always a capital letter and it is represented in a capital letter. In hole basis system, the H letter will always be in capitals and it is going to be constant throughout the process, whereas the shaft areas alone will be modified. Now you have to complete workshop number 7. In workshop number 7, you have to find out the limit dimensions for an interference fit. The values for the fit and the shaft basics dimensions are already given. In a similar way, you have to work on the problem number 2. Once you completed your problem, you can verify with the completed sheet as available in ORG. With this, we complete this lesson on how to apply tolerance and the dimensions. In the next lesson, we are going to see how to apply the GD&T symbols for this tolerance areas.